Okay, colleagues, let me perform some pre-final recall. So we have here Lipko Ivan, we have Sergey Dubovik, and sorry for my pronunciation, Jihad El Sana is understood. Yes. So please.
Yes, Ivan Lipko here.
Okay. So please, could you switch on your mic, Jihad, please? Probably just 10 minutes left. That's why he's not. And the second one, the third one, I think. Could you switch on your microphone just to check the connectivity? Hello? Okay. So still we have 8 minutes. So we will wait for other participants. So 8 minutes left. So see you. So, ladies and gentlemen, okay, so we will start our O2, O1 and O2 sessions, so which means we are online. Please, those who now is online, please, it's a final recall. I need to understand who are here to present the reports. So please switch on your mics and, if possible, switch on your cameras.
Ivan Lipko, ready.
Okay. So it looks that others have some technical problems probably. So I think we will start from you, Ivan Lipko. As the chairman and the moderator, I need to announce you now. So okay, so your presentation is called monitoring dynamic systems with a tipping based on the principle of large deviations. Please, you have a floor. You may, yes, exactly. So share the screen, please. You can start.
Okay, good day. Dear participants of the conference, my name is Ivan Lipko, and I am presenting you a report of the topic monitoring in dynamic systems with typing based on the principle of large deviation. I am research from Sevastopol State University.
Okay, excuse me, could you just open in a presentation mode, because currently we are seeing your PowerPoint. Yes, F5, F5, I think, yes.
Так.
Yeah, presentation F5, I think.
Okay. Is it good?
Well, it's of course it's cinema, but it's not a presentation mode. Is it possible?
Okay. This, yes.
Yes, exactly. So, excuse me, you may proceed.
Okay, this is presentation on the topic monitoring in dynamic systems with typing based on the principle of large deviations. The presentation is devoted to monitoring of such climatic phenomenon as El Nino. El Nino is a quasi-periodic climatic fluctuation that has cold and hot phases. El Nino is associated with a band of warm ocean water that develops in the central and east central equatorial Pacific Ocean. The dynamics of El Nino is similar to the dynamic as in van der Pol equation, with alternating stable and unstable manifolds, also known as bifurcations. In the literature, such behavior is known as B-typing, bifurcation typing, qualitatively change in the behavior of the system. Such dynamics is characterized by mixed mode oscillations with multiplied time scales. In the picture below, on the left, you can see the temperature fluctuations in the El Nino model, which developed by Jean and Timmerman. We use this model in our research. On other pictures, you can see statistical data from North Ocean America Statistical Agency. On slide three, you can see a system of differential equations that describes the so-called normalized El Nino model. X, Y, and Z are normalized values of temperature and thermal index. If X, that is the temperature difference, is greater than 1 degree or 1.5 degree, then it is considered that El Nino has begun. Big T2 and T1 are east and west surface temperature, small h1 is a thermocline death of the Western Pacific. The equilibrium state of this unperturbed system is a saddle focus, which an unstable oscillatory component and a stable a periodic motion. And so El Nino South Oscillation mathematical model is a weakly perturbed and weakly stable system. Saddle focus point shown on the right in 3D, three-dimensional. On slide 4, we show the sensitivity of the solution of this differential equation, sensitivity from the initial condition. The upper figure is the temperature change, and the lower one is the depth of the thermocline. Two cases with different initial conditions are considered. The difference between them is only in the depth of the thermocline. In the first case, we observe El Nino with a big difference in the temperature, and in the second, we do not, just because the thermocline is a different depth. On this slide, we show the problem we are solving. The problem we are solving is related to the prediction of when a deviation from the amplitude of the normal deviation will occur at big time THR, T threshold. And when a large deviation LD large deviation will be achieved. When this time, the value of time is not large for T threshold, and this stage noise, and on this stage noise plays a big role, and the time of large deviation is small, and we can do its estimation without taking noise into account, only by solving the initial problem. The key to solving the problem is to answer the question: what is the most likely, most probable trajectory of the movement? To solve this problem, we to solve this problem of determining the most probable path. For equation 1, we construct this deterministic equation 2, and then minimize the problem 3 with functional 4. Functional 4 named as action function. The meaning of this problem comes from estimating the probability of reaching the set big D, to which the system can move under the influence of small perturbation. The corresponding theorems are considered in the theory of large deviations, in particular by Wenzel and Fredin, Soviet researchers, and our contemporaries Eric Vanden Egenden, Freddy Bouchet, and Tobias Grafke. The basic equality is contained in equation 5. X star is the most probable trajectory, since unknown disturbing internal mechanism of the El Nino phenomena spend less energy to reach the threshold X threshold. Action function, equation 4. Action function describe something like energy. Slide 7. Thus, in order to find the start time of large deviation, we look at a linear model of the system and can analytically obtain the most probable trajectory, equation 6, and the probability of occurrence of this state. If the probability is high, then the time has come. The time of super large deviations, big T LD, large deviation, is found by solving the initial problem with initial in X T threshold. On this slide, we show you the results. The trajectory, most probable trajectory X star in red, compared to one El Nino oscillation. And a similar result can be obtained by Monte Carlo method on the right picture. The density of trajectories shows the most frequent visit to the phase region. They are similar to instanton, to most probable path. And in conclusion, we can say that we have considered the dynamics of the non-linear system of the El Niño phenomenon. We have proposed an algorithm for predicting the behavior of the system based on an assessment of the probabilities of movement along the most likely path. How it relates to intelligent systems? It is based on the knowledge about the behavior of the system. We get this knowledge from the model with help of probabilistic approaches to solve the problem, which are based on the theory of large deviations. So we use data to construct the model, not the knowledge, like in machine learning or AI. So I finish. If you have any questions, I'm ready to answer.
Okay, thank you very much. Any questions, please? Now we have time for questions. According it is online, we may wait for some time. Okay, I have one question from my side as the chairman. I will ask you. So you're from Sevastopol State University, as I say. Yep.
Yes.
Okay. So do you use in your work satellite information, which comes from satellites from world meteor satellites like this? So in your
Really not. I use statistical data of El Nino, which you can download from this site. This is official. Here below is official
Yes.
statistical system of El Nino, and we use only so-called El Nino index data, not temperature directly.
Well, actually, so that I see that it's from NOAA.gov website, and this sea surface temperature, probably it also comes from a satellite called NOAA, because it has these satellites has many sensors, including, for example, land surface temperature, the sea surface temperature, and then it is good to use like VRMF model also. Do you use these models in your work currently?
No, we do not use any of these of satellite models, but I agree with you that this data is very useful.
Okay, thank you very much for your talk. So please stop sharing your screen, and we will come to the next presentation. I think let's recall Justin Diamond. Is it here? No. Okay. Imad Ali Shah and other participants from Pakistan.
Yes, I am present.
Okay, nice to hear you. Is it possible to switch on your camera just to say hello to us and to those who with us in okay, nice to see you. Well, if you already know how to share your screen, you may start your presentation.
Okay. Should I keep my video also on or not?
It depends on you. Well, you may turn it off or, well, whenever you like. It depends on your GDPR and so on. Nice. Okay.
Is it visible?
Yeah, it is seen.
Okay. Okay, so today I will be presenting our research titled SFA Unit, More Attention to Multi-Scale Contrast and Contextual Information in Infrared Small Object Segmentation. We are researchers from National University of Science and Technology, Pakistan, and we were in collaboration on this project, the two departments that are electrical engineering and computer and software engineering. So let's start. Today, I would like to shed light on the profound significance of infrared imagery and infrared small object segmentation, or let's say ISOS, in various critical fields. So starting with infrared imagery, it offers unparalleled capabilities. Starting first, it boosts in all weather capabilities, such as in fog, rain, snow. It ensures visibility even in the harshest condition. Secondly, it grants us a night vision, enabling us to navigate and operate in low light or pitch dark environments. Furthermore, it excels the heat detection, allowing us to spot temperature variations. That is a crucial tool or task in the research, especially in the rescue missions or identifying the concealed objects. In addition, infrared imagery has the unique ability to conceal, camouflage, unveil objects, or individual hidden to the naked eye. It is also used in environmental studies as well as in the medical field. In last 1 decade, it has been seen that in the security and surveillance, the infrared camera has been vastly used for ensuring around-the-clock monitoring and detection in the darkest hours. So as you can see in the images, we can use the infrared images to detect any drones or any equipment that is of the security nature or to be tracked or detected. So this brings me to the infrared small object segmentation, which is our prime research domain. And we like to work on enhancing the target detection system so as to help the early warning systems, and that research can be used in any maritime or any military applications, or in the search and tracking rescue missions, or into the navigation and autonomy. This brings me to the core point of our research, and that is that the infrared imagery as well as infrared small object segmentation in the infrared imagery provides invaluable capabilities for a wide range of applications that not spans from security and defense, but also to the medical, the environmental, and the natural detections and remote sensing capabilities. Let's discuss some related work. If we see the related work in the image, the infrared small object segmentation, previously there were traditional methods to mitigate for the segmentation of the objects to be segmented out. And in those, mostly the applications were mostly traditional filters, which included top hat or the combination of such basic filters, which included max median or the max mean. And as the time further processed, there were different kinds of algorithms which worked on the rank-based system, which included the principal component analysis or the LCM-based techniques. But however, these techniques have a core issue, and that is that if you have to apply any traditional filter or any digital image processing based technique, which is classical in nature, so you need a prior knowledge of your environment. And it is also the main issue to these approaches is that they are not very good with the generalization of the generalization of their domain. So for the if we see for the last 1 decade, especially after the success of AlexNet, deep learning architectures were very successful in this domain, and especially the CNN since 2012. And subsequently, with CNN's vision transformers also were introduced in 2017 and 19 respectively, which further enhanced the capabilities of our computation as well as our accuracies and the performances of the models to effectively segment out the necessary or the goal targeted approaches. As we can see, there are different kinds of deep learning approaches, which includes UNet, the future pyramid networks, the SEM, ALCs, and there are a number of research were done in the ISOS domain. However, the core issue which remains and is still prevalent is that there is lack of effective utilization of contrast and contextual information to extract information in the local contrast as well as the global contextual environment. And another issue with the deep learning model is that when small objects are required to be segmented out, then as the model is increased in size, as the depth is increased, we see that small objects are potentially lost. So, and this also brings me to the third main point, which is seen in ISOS domain, and that is that when we have to segment out small objects, so it is very difficult to differentiate between a noise pixels and a small object. For example, if the size of an object is like 3 by 3 pixels, so it can be easily confused with a noise pixels. So this third point is also very important to retain the information of the small object while we learn and while we go deep into the network. So before I move on to our approach, the dataset that we used for ISOS domain research were two, and that are SIRST and IRSTT. The details are as flashed. The dataset of SIRST contained 427 images. It consists of low contrast and heavy cluttered objects, but the number of different or various kinds of objects are not present. Coming over to the IRSTD, it is more diverse in terms of the shapes and the complex background that it has. So we evaluated our work on these two datasets. The image size that we used for our model, that was 256 into 256, and the data split was 8:2. That's training versus the validation. The last two images are from the SIRST and IRSTT datasets, and you can easily see that for a human eye, it is possible to differentiate, but it is very difficult when we have to apply some classical image processing techniques to segment out these type of images, which are important to detect, especially in terms of the surveillance and military applications. So before we started implementation of our approach and the segmentation models, we started with the evaluation step, and that was that we worked on enhancing the infrared images using traditional image processing techniques. We actually started with original infrared image from the SIRST dataset, that is the laptop image, and then we applied the SCAR and Sobel convolutions. You can see the highlighted two images are the results of the SCAR operator and the Sobel operator. Now, if you see in depth, the Sobel operator is giving more of the unnecessary artifacts that we need. So, and as compared to the SCAR operator, it was performing a bit better. Then we applied the fast Fourier transform so as to have the global contextual information into our system also. So these two are the subsequent results of the previously SCAR operation and Sobel operation, and afterwards applied a fast Fourier transform. And at the last, these two highlighted, the upper one and the lower one, are the results. Now, if you see, the bottom one is the top one is the result of the SCAR convolution, afterwards a fast Fourier convolution, and concatenated together and then normalized. So as compared to the bottom image, you can see minimum artifacts. So this gave us the insight to get this approach into the deep learning model. The reason one was to give the local contrast information to the system, and as well as give the contextual information. The contrast information was given by the SCAR operator, whereas the contextual information was introduced by the fast Fourier transform. So this brings me to the proposed method that we used in our research. the core backbone of our proposed approach or architecture is the unit architecture with attention gates. But we had a little modifications in the proposed model. Now, first is that we used the attention gates in the encoder blocks also. If you see the unit architecture, initially it has 64 depth. What we did that we split that encoder block into two, and then we had a cross attention mechanism into each encoder block. And now let me explain each model in the next slide. Now each module is as flashed. What we did that, as already discussed, the SCAR operator-based convolution and the fast Fourier-based convolution, these were used in the encoder block as well as in the decoder block of the original unit architecture. Though these blocks are shown on the left side, as you can see. Now coming over to the SCAR convolution and the fast Fourier convolution, and how we actually implemented it. That it was that it takes the input image while being in the encoder or the decoder block. It applies the SCAR convolution as well as the Fourier convolution in parallel, and afterwards it basically what it does that it is concatenated and then it is continued in the encoder block. Similarly, the attention gates are the classical attention gates that have been proposed in the original unit architecture with attention gates. So this is the core modification of our research. And now coming over to the experimentation. The experimental settings were that we used our loss criteria to be binary entropy loss with optimizer of Adam weighted that has had 0.001 learning rate with a decay rate of 0.004. The batch size was kept 8 and epochs were used 150. The platform that we used basically the Google Colab, which provided us with P100 GPUs and 32 GB RAM. The evaluation matrices that we used were of 3 levels, and the first one was pixel level, the second one was object level, and then the model level performance were evaluated using these 6 matrices. In the pixel level, we use the intersection over union and the normalized intersection over union, whereas in the object level, we use the matrix of probability of detection and the false alarm rate. The model level was evaluated using F-score and area under the curve. So coming over to the quantitative comparison and the quantitative results with respect to the model level matrices is as shown. Now, if we see and we evaluate it with the latest deep learning based architectures, our proposed method performed significantly well, and the results are as shown. So coming over to the quantitative comparison with respect to pixel and object levels. So if you see, our model was very good in the pixel level extraction of our objects, and it has done very good and very significant with respect to other approaches. There are some issues with the probability of detection and the false alarm rate. The evaluation was compared with the UCF net recently being published in CVPR, that they had better object level results in comparison. But if we compare the result in comparison to our pixel and object level, the difference is minimum where they outperforms, but where we are outperforming, that is a significant approach, especially in the pixel level approaches. But if you see the IRSTD, as already mentioned, that it is more complex than SIRSTD. Here, we our proposed model has better probability detection. So this signifies that our proposed model is working better as compared to the other architectures, especially in the complex scenarios. Coming over to the qualitative comparison, so this is the first image example. On the left side, it is the original image, and below it, it's a true mask given in the dataset of SIRST. So the results of the top hat, the IPI approach, the ACM, ALC, and if you see our proposed at the right bottom corner, it is more enriched with the fine details of the object being detected, and the shape is retained. And we do not see the false detection is here. It is significantly better than the other results. Now, coming over to the second example from the IRSTD dataset. Now, here, if we see again, even in the complex background where the object is a bit dull than the region. In the original image, you can see that it is the object is not as brighter than the background. Even then, our approach has significantly segmented out the necessary details of the small object and have better shape and is better correlated to the true mask. So, in conclusion, we identified the prevailing issues in the ISOS domain that has been observed since quite a long time now. We proposed the SFA unit that is basically a modified unit with attention gate based architecture, and we introduced SCAR and fast Fourier based convolution block into both encoder and the decoder blocks of the unit, and also introduced vertical attention gates for more information flow. Now, this modification gave us provided and helped us with giving multi-scale contrast and contextual information out of the infrared image. And it also helped us to address the low information in small object, as already highlighted that small object can be easily confused with the noise pixel being small, and also the potential loss of small objects in the deep learning models. This modification was evaluated a number of times, and we achieved a significant improvement by combining all the matrix results and averaging them out. The result is of 5 parallel runs, and it gave us better results in comparison to the existing state-of-the-art approaches. Now, this SFA unit gives the insight to more research in the ISOS domain, and also give the insight to work on the classical image processing techniques and bring the contextual and the contrast information to the deep learning model. So where the deep learning models have the weakness of losing the small object and have the lack to effectively extract the contrast and contextual information, we gave those back in terms of the image processing filters into the deep learning model. So this is bring me to the termination of my presentation. If there are any questions, I am here to answer. Thank you.
Thank you. Thank you very much. Okay. So yes, we have a question, please.
Dear Ahmad Ali Shah, what about computing resources, computer power of the inference system? What can you say about this?
Okay. If we see in comparison to the transformer model, it is better in the computational requirements. If you see the depth of the depth and the number of encoder blocks and decoder blocks that we have used, it is equivalent to the original unit architecture. So the additional computation that is being introduced in this model is just from the scar calculation and the fast Fourier transform. So those computational requirements are not as significant especially transformer based applications. And if we compare to the I have a comparison with the UCFnet. They have like 5 levels. So we are working on like three encoder and decoder block layers.
Okay, thank you. If you let me, second question.
Okay.
Yes, no problem.
What about convergence? How it fast when you learn, when you train your model? Some comments, please.
Yes, sorry, I did not have shown my convergence graphs. The convergence is likely within first 50 to 60 epochs. The system goes into pretty convergence state for SIRST, and around 80 to 90 epochs for IRSTT dataset, which is more complex.
Okay, shukran jazilan.
Okay. So any other questions, please? So we have none. Thank you for your presentation. Actually, so your research quite nice. It was good presented, because you have had to compare the traditional appropriate methods and to find your niche, and so present us the final results. Thank you again.
Thank you.
Okay, so let me proceed as the chairman with our schedule. Currently, I think that we still have no Justin Diamond from Switzerland, and probably we have no also the presentation about RMNet residual and multi-scale feature fusion network for high resolution semantic present. Okay, so that's no. Well, please, I see that Mr. Yang Kiju is connected to our system. So you have a floor to present the presentation HRJC YOLO for urine sediment practice detection in high resolution microscopic images. So you have a floor now, please. We're waiting for you. Okay, nice.
Yes.
Good day.
Can you see me? Yeah. Hello. Can you hear me?
Yes, it's already evening. Yes, for you.
Okay. So
yes.
Let me see how to.
Okay, you may launch your presentation. Yes, and then find again delete. Yes, we see your screen.
Okay. So you are now seeing my slide, right?
We have your site, because you duplicate the screens. Now you need to start your presentation, because now we've seen.
Okay. Thank you. So, Mr. Chairman, ladies and gentlemen. Okay. Good afternoon. Sorry. Let me do something first.
Yes, please.
Okay.
Yeah, but could you share your presentation, because we see the screen exactly with the platform. You need to change.
Okay.
You need to change the screen.
Okay. Let me do it again. I think it's this. Oh, sorry.
No.
Okay. I know how to do it. Okay. I think it's this. Okay.
Yes. Now it's okay.
Okay.
So you have a floor.
Okay. Mr. Chairman, ladies and gentlemen, Good afternoon. I am very glad to have this opportunity to attend this conference. The topic of my presentation is HRGC YOLO for urine sediment particle detection in high-resolution microscopic images. So first, I want to briefly introduce urine sediment particle detection. First, it plays a pivotal role in diagnosis of renal and urinary tract diseases. And to get a sample of urine sediment, the urine samples are centrifuged, which is then placed on a slide for microscopic analysis. According to the relevant reports, urine sediment particles can be classified into 6 categories, including erythrocytes, leukocytes, epithelial cells, casts, crystals, and pathogens. At present, the detection method of urinary sediment is still mainly based on manual microscopy, which is labor-intensive and subjective. And recently, convolutional neural network-based object detection has witnessed rapid development, enabling swift and accurate detection outcomes. However, I'd like to say current methods for detecting USP images face 2 major challenges. First, urine sediment particles exhibit intra-class variation and inter-class similarity, leading to classification confusion. As we can see in the images here, there exists a large morphological difference between these 2 objects, but they are all categorized as uric acid crystal. And both of these objects are circular, but the left one is the spore of fungi, and the right one is normal erythrocyte. Secondly, fine-grained information in high-resolution USP images is inevitably underutilized owing to the memory limitation of inference devices. So to alleviate these challenges, we proposed a novel high-resolution global context HRGC YOLO model. And we introduced a tile-based image processing approach to effectively exploit the fine-grained information in HR images.
Excuse me, probably we have some problems with the connection. So we have no sound currently. Yankee, could you write a message, because I can't understand. So do you hear me now? Yes, probably we have some connection troubles, I mean, with the sound, and even probably with the presentation, because it's frozen. It's just frozen. Please, Yankee, probably also he can't hear me now because probably the problems is only on that side. We need to wait for a couple of minutes, or well. Okay, I will probably just to fill the pause with some let's say not advertising, but I need to share that well, yeah, trying to share my screen and wait for our Chinese colleague. Do you see my screen now?
Yes, the online session.
Yes, exactly. So what I'd like to see to share that I'm just trying to say that okay, this is a e-schedule. You already know about this, and I think that just this evening or later, tomorrow morning, we will have here a new button, and you can download proceedings of our conference from the website, as it was in the previous event. If it comes to previous event, you see it is like a platform, and you can just browse and see what results were during that event and go to the proceedings, and also you may go to a program and find all the plenary sessions and information about colleagues who had presentations. And we actually saw there we had very nice conference with presenters of all over the world. It's around more than 10 countries, and it was a special session which we called GIANT. It's a national, it's pan-European network for research education, global network, and we had a presentation from European Space Agency. We have presentation also, plenary presentation from nice guys from USA, for example, Andrei Gabrilian, or let's say the second day it was Ruslan Salahudinov, who was actually led let's say artificial intelligence department in Apple. Well, and as for proceedings, I think that we will have the same proceedings. I mean, the way of presentation of these proceedings this time. So you will have a chance to find your presentation here, or so while browsing this let's say table, and find exactly your paper and watch exactly your presentation like this. So that is like not advertising, but I'm sure that it was a start for a new platform, the way how to do it online. And now I will stop to share my screen, and I hope that I think no. So we have no, unfortunately, have no reporter from China. Yankee, who just started to present the paper, his presentation. Probably we need to go to the next presentation. And so please, we have here Mikhail Kharinov. Yes. Do you hear me now, Mikhail? Okay, so we can still be online here. If you want to share any presentation for among those who are in the system, please just tell some words. You may share your screen and tell whatever you like, because we have time now. Or in other case, I will close the session, because unfortunately, currently someone experiencing some troubles. Other presentations. Okay.
Dear Chairman, can you share YouTube link of this online broadcast?
Okay. Yes. It's simple, because actually, so it's also on the website, but of course I will share it.
Oh, thank you.
Yes, it's on the website, and it's just very simple. So, Mikhail, could you switch on your microphone, Mikhail Kharinov? And because because you have a chance to now to present your paper, present your research. Unfortunately, no. So in this case, I will close this session, and those who still haven't present your research, please, you may. Oh, Mikhail, so you switched on your microphone.
Yes, I'm online also.
I hear you, but I don't know what to do.
Okay, so I'm online right now. I can present
Start my demonstration.
Okay, please, Mikhail, could you
Can I present my work?
yes. Oh, Mikhail, so wait a moment. We will come to Shirat Sana, and you may present your work now. So
Okay,
please have a floor, Shirat Sana.
How to share screen?
Yes. Do you know how to share the screen?
I'm trying now to learn this.
Okay.
So 1 minute.
It is the third button from the left side, a screen with arrow.
1 minute. Let me see if because I have the presentation in different screen. Exactly. I just okay. Let me see. Now do you see my presentation?
Exactly. We see your presentation, the first slide.
Okay. Good afternoon, and sorry for the delay. It's actually has just like some kind of a internet disconnection. So in this work, I'm presenting part of ongoing work, actually in providing a approach to a health assembly or disassembly maintaining of appliance using augmented reality. And this part is focused in hand action recognition. So this was a joint work with two of my master's students at the Department of Computer Science at Ben-Gurion University. And the main idea that, think about like the idea now we want to maintain our like devices like cars, appliances, and all these things. Usually we wanted to call a technician or a mechanic, even for small maintenance, and the lack of these skills, technicians and engineers, make kind of like the high cost for this maintenance. Usually we need to wait long for these technicians to come and to do and fix our devices. And one of the idea here is to try to provide a augmented reality based system that can address this challenge. And the main idea is actually based on the idea that we imagine that the technician will come one time and will fix our appliance, and then we will take this video and process it and create what we called actually a work execution file. And then we can upload this file to an augmented reality device, and it will actually guide the maintenance or the procedures from A to Z by providing augmentation on the device itself. In order to do that, the first important procedure is actually to detect the hand action. So we assume this technician will have a head-mounted camera or a chest-mounted camera, and he will be performing the action. The recording of this video then will be processing to create this kind of like this file that will help execution this procedure. So in order to be able to detect this procedure, these actions, what we call hand action recognition, we have in this paper, we present a new data set which include videos, short videos of various actions that show a hand actions while maintaining such devices. Then we will present a way to extract features that include the hands and the use tool and the device component or the part of the device component that manipulated. And then this will be integrated in what we called a saliency mask that will allow the deep learning model to focus on this area. And then we developed a transformer-based approach that detect and recognize these hand actions. So the data set we created is what we called VML. This is our lab, Visual Media Lab, is actually VML working hands. The main idea to be able to recognize all these various actions. So we detect the tools, we detect the hands, and see this is, for example, unscrew. This is another approach of unscrew. This is clip. This is, for example, cut. And so this the first is a part of our research is we prepared a data set. The data set was recorded from camera that mounted in the head and the chest. And the main idea that it shows the hands or the operation from a first person view or first person perspective. And this is simplifying in some sense the problem, but it's also complicated the problem because the camera is also moving. And we focus in actions or hand actions that we apply in maintaining mainly assembly, dismantle or assembly mechanical devices. So we created 12 action categories just for presentation purposes. And with these videos, for each one, we have its category. And now in the category, we have, for example, screw in, screw out. We have how many hands this action used for. To summarize this, we say it actually could be screw in, screw out, could use one hand or two hands, and it could use screwdriver or spanner or wrench or Allen wrench or electric screwdriver. The same thing with hammering, so it can use, like the action is hammering, which also the category. It uses usually one hand. It actually could be a hammer or a melt. Sometimes action we see that has no tools, and this is the data set. So we created, like, if we see from the first category, we have 569 categories, the second 250, and so on. So practically we have more than several thousand of video. Each one is several seconds, which started with just the beginning of the actions. We have kind of a start, and then the one action, and then the end of the video. Since we also integrate with this what we call another saliency map that we will show how we computed this. And then we developed a deep learning model, which based on transformer, that actually include several components. So the main component, what we call the feature extractor component, that extract features from the hands and the tool and the working area, which I'll explain a little bit later. Then we feed this to a transformer encoder, and then the output will pass through fully connected neuron in order to detect the action. So I'll just go into detail to see what we have, what we will do with this model. But first, I will see, for example, we subdivided our data set in 20% for training, 70% for training, 20 for testing, and 10% for validation. We also applied various augmentation techniques, such as changing illumination, color, planing, various level of blurring, rotation, small angle, usually horizontal, shear, and like by small angle in order not really to dramatically change the video. And after how the model itself is defined, as I explained earlier, the feature extractor started by identifying the hands and the tool. So we see in A, here is the video frame. In B, we detect the hands and the tool. We look at the bounding boxes and the region where the tool is actually working. Now, it's not always possible to detect the tool, like the working area, the manipulating component. But we assume toward the tip of the tool, there exists the manipulating device. The second thing, we bound all this area, but we called a action area or action region. The action region actually define the area that we would like the deep learning model to focus on. So, which is the ellipse that bounds all these components together. Then we create a mask. This is what we call a saliency mask. The mask will have one within the circle and faded as we go away from this bounding ellipse. So this is, as we see in D, this is the saliency mask. And this is one part of the feature extracted component. So the feature extracted component will include the feature we extract from the model, and then we will generate the mask, and this mask will be multiplied by this image, as I explained before. And this will be fed into a CNN model that extracts the feature from the image, and the mask will help it to focus in the action region. In addition, we extract the skeleton from the hands and the two hands and encoded this into two vectors, left hand and then right hand. If there is a one hand involved in the operation, we will have 0 for the second hand. We detect the right and the left hand. And in the same time, we assume there is only one person working. And this setting, we assume we have at most two hands. Then the output of this will be one feature that came from the CNN model, and the another feature, a part of the vector, will came from the skeleton. We concatenate this into one feature vector that we will call this the feature A vector. And after we have this, practically what we do, we take the video input from each action, and the training procedure we extract from each frame, we extract the feature vector for each frame. Or practically, we have a sequence of a frame. We have a started symbol that actually start of the action. And then we have a position embedding in order to create an order between these vector. And this will be fed into a transformer. We actually use only the encoder part. Now, the output of the transformer, the encoder part, will be one vector. Now, we feed this vector into fully connected neural network in order to determine which one of the actions. So we determine the category and the action as I explained in the previous table. Now, we have implemented our approach using Python and PyTorch library. For hand localization, we use the YOLO model. And for detection the hands and the skeleton, which is the landmark in the hand and the skeleton, we use MediaPipe, which will provide us with the skeleton and the landmark. We extract the features with the CNN. We adapted the VGG19 just for simplicity. And we also assume the hands and the important features are nearby. And this is why we started with a VGG19 pre-trained, but we allow it actually to adapt during the training. So practically we have VGG pre-trained, but we don't freeze it. So this is indifferent. So we don't retrain YOLO, we don't retrain MediaPipe, but a model that extracts the features from the frames we start with a model that was pre-trained, but we allow it actually to participate on the full end-to-end training. So we train the model for 300 epoch, and then we evaluate the precision and recall, and we get very impressive results. So the model show a high accuracy, as we see from the confusion metrics. We practically get almost 100% for some of the actions. and we get like sometimes like 67%. And as we see from the confusion metrics, usually the off or the error are not really far away actions. They could be actually nearby. Now, this is one of we test this in our data set, and this was the result on our data set. But actually, as I said, we have 70% for training, 20% for evaluation, 10% for testing. This is practically what we have done. I think we get a good result. One of the things we are in the future work, we plan to, but I would like to conclude before I go into future work. So we introduced a novel data set for detect hand action related to mechanical devices. Remember that this work focus in mechanical devices, and we mainly, the actions are involved, the actions that may involve in assembly or dismantling such devices, like taking off one part or putting on another part. And this is usually when we come to fix a car or appliance or these things. The other thing is actually the description of a innovative model, which based on transformer architecture. And the data set, as we said, actually we have 12 distinct categories. The first person view, videos. The videos range from 2 minutes, from 80 frames to 300 frames, practically from almost 3 seconds to at most something like 10-12 seconds. And this is one of the ideas that we don't right now simplify the video. We take the entire video, but we focus on the iframes that we get from the video segment. The model we presented also provided very good results on our data set, again, which is, I say again, which is not really means that it work for the real world. This is the future work. We want to extend this to be able to test it on kind of another, like sometimes when you don't have the tools are not really that clean and the region is not really clean. If we are thinking about like applying these actions to, for example, garage or fixing a car, usually we'll have a oil or grease or dust. And this is part of our future work. But so far, I think we presented a very impressive data set, good result for the model we used for training. And that's it. Thank you. And I would be happy to address any question.
Thank you very much for your presentation, and thank you that you finally with us. Thank you for your excellent results. Please, colleagues, you may ask a question now to our colleague.
I got one.
Okay, you may ask.
Oh, okay. Thank you very much for your nice presentation. So you reported sort of multi-step, multi-methods procedure. Typically, this is difficult to somehow learn to train them. And you need a lot of data because different steps needs different data, etc., etc. So do you see it is possible to solve the problem, your task, using just a more straightforward approach without that multi-step, multi-sort, etc. things? Thank you.
Thank you for the nice question. Actually, we try to use a practically more simpler approach, which is based only in the skeleton, and try to use features from the skeleton of the hands. It turned out that it's almost impossible and very hard to get good result unless we combine a kind of description of the hands that include features that are not encoded in the skeleton. This is what we extract using the CNN. The used tool, which is also part of this, and in the same times the region of the operation. So it's somehow the relation between the hands. And remember, we have a lot of data. We have between 80 to 300 frames, and we have frames for each video segment, and we have more than like 2,000 videos. After augmented, we reach something like 5,000 segments, video segments, and about 80 to 300 frames. This is a lot of data. The training for 300 epoch in a machine that have like GPU, the most advanced with a very large memory, take like, I don't like recall, but the students told me that more than a day. And this is why it's actually, I agree with you, it's a huge model, but I think the result this model provides is completely way above the simple, straightforward approach.
Thank you.
Thank you for your answer. Any other questions?
Sorry, maybe one more.
Yes, of course. We have time.
Or perhaps I miss the point about augmentation. Is this image-based, like image-like augmentation or video-like augmentation?
This is a very good question. It's actually both. We need to augment the images, but then we need to maintain temporal coherence among the consecutive frames. So if we decide, for example, to illuminate or change the illumination level within the video, it's actually for the entire video. It's the same change. If we decide, for example, to blur the video, we apply this for all the frames. If we plan, for example, to rotate the video, we rotate the entire frames of the video with the same small angle. If we plan to shear, the same thing. So it's actually both, because we apply every augmentation to frame, but we maintain the temporal coherence.
Yeah, certainly.
Yes, exactly. Okay.
So you say,
Yep.
for example, or par example. Sorry, I'm just
Go ahead, yeah.
kidding a little bit.
Okay, yeah.
Thank you.
Thank you for your presentation and for answering questions.
Thank you. I was hoping actually to be in person and actually registered to be in person, but since the flight from Israel was canceled, I was not able to visit Minsk, and I hope for the next conference
Yes, exactly.
I will be able to visit Minsk.
Please stay with us. You may see these sessions on YouTube, and you may go on the online page of our website, and you can connect to any of the sessions. So today and tomorrow and after tomorrow, and of course also with big hope for future in-person, well, let's say communication. Okay, now we will proceed with the presentation, which was actually delayed because of the connection problems. And please, Dr. Yankee, you may proceed with your presentation.
Okay, thank you. First, I want to apologize for the connection problems.
Well, it's not your fault, of course. Okay, you may skip these slides if you'd like.
Okay.
And
Okay.
yes, exactly.
I think I end up this part, right? And I will continue in this part. So, yeah, actually to alleviate the challenges we mentioned before, we proposed a model called HRGC YOLO, and we introduced a tile-based processing approach to exploit the fine-grained information in HR images. And we integrated the long-range dependency capturing module GC block into the original object detection architecture. In this work, we chose the YOLO V5 model as our baseline. The GC block here we use is similar to attention module, and previous study have proven the effectiveness of their ability in alleviating classification confusion in USP detections. However, those adopted attention modules such as squeeze and excitation module and convolutional block attention module predominantly focus on local spatial information and overlook the significance of long-range dependencies. And we observed that by incorporating non-local attention modules into the network, it will improve the detection accuracy more effectively. We believe that it enables the model to compare confusing objects with other similar objects in the image, resulting in more reliable and reasonable results. The mathematic mechanism of GC block is illustrated as follows. The structure of GC block can be defined as a combination of simplified non-local block and the SE block. It has the ability to integrate and analyze regions of interest across the entire image. Next approach we used is the tile-based image processing. During our collaborating with the hospital, we find out that most of the urine sediment images have very high resolution, such as 5,440 by 3,648. And if we directly input high resolution images into our object detection model, it will cause memory overflow as well as slow down the training process if there exists complex data augmentation procedure. In a general way, we can roughly rescale the HR images into smaller size, but it will lose the essential fine-grained information. And to preserve such information, we apply the tile-based image processing approach. It will crop the original high-resolution images into several square patches. And during the training procedure, these patches are fed into the network along with the compressed original image. So these are our solutions for the two challenges in detecting high-resolution urine sediment particles images that we mentioned before. And before I share the experimental results, I want to make a brief introduction of our manually built high-resolution USP images dataset. To conduct an evaluation of the HRGC YOLO model, we manually built a dataset consisting of 1,278 HRUSP images. These images were at a magnification of 400. The majority of the images have dimensions of 5,440 by 3,648 and 4,000 by 3,000 in pixels and were saved in TIFF format. Our dataset consists of 8 classes of particles as we show in the right pictures, with a total of 32,968 particles manually labeled by clinical experts. The left table provides a summary of the dataset illustrating the number of instances in each category. We used 903 images for training and 365 images for testing. Here we present the experimental results of the comparison between GC block with other attention modules. In summary, the utilization of attention blocks consistently enhanced the detection accuracy of the model. And compared to other models, the GC block demonstrated superior performance. Our model achieves a 1.6 higher mean average precision compared to the baseline. These results highlighted the advantage of the GC block in capturing global contextual information, particularly in the detection of high-resolution USP images. Moreover, the GC block introduced only a marginal number of additional parameters and G-flops, ensuring that the computational burden remains manageable in practical applications. After that, we compared the detection performance of HRGC YOLO with other detectors that are commonly used in natural images. Here we chose 3 recently released updated YOLO models. To further improve the detection accuracy of HRGC YOLO, we additionally used the focal GILU bounding box regression and SIM-OTA label assignment strategy during the training procedure. The results of ablation study and the comparison between the YOLO series can be seen in the table here. The most exciting conclusion is that our model outperformed all the other models in the HR USP image detection. The detection performance reflected by the MAP50 value was improved by 4.5% compared to the base YOLO V5 model, and the tile-based approach exhibited a notable impact on the detection of small targets that are inherently challenging to detect. And the ablation study confirmed the significance of the tile-based procedure and the GC block we integrated in this model. And however, we also noticed that the inclusion of the tile-based strategy in YOLO V5 and GC YOLO reduced the detection accuracy for large-sized objects. As a straightforward approach, we believe this shortcoming will be addressed and rectified in the future. And this figure here can reveal the characteristic and advantages of our proposed methods in a more intuitive way. HRGC YOLO and GC YOLO have more advantages than the general object detection model in detecting small objects and dense objects, especially with no obvious structural features, and the inclusion of tile-based approach further improved these abilities. But unfortunately, it has to sacrifice some of its ability to detect large objects. In conclusion, our proposed method, HRGC YOLO, demonstrates exceptional performance in accurately identifying and categorizing USPs. We employed a tile-based approach to preserve and utilize fine-grained information in large-scale images to ensure that the detection accuracy for small objects. And the GC block we integrated effectively captured long-range dependencies and enabled the model to handle complex spatial relationships within the image. And the evaluation that we carried out upon the manually built dataset showed that HRGC YOLO outperforms other general object detectors in detecting USPs. And that is all my presentation. Thanks very much for your attention.
Okay, thank you very much. Finally, we come to end of the presentation, and now we have a couple of minutes for questions, even due to our tough schedule. Again, so please, any questions? Okay, we have none, and now we have a presenter who will ask for a presentation, which is actually in the program. Okay, Mr. Jiruf Shen, sorry for my pronunciation. You have a floor because you have we missed your turn. Now you have a floor. So about RMNet, a residual and multi-scale feature fusion network for high-resolution image semantic segmentation. Please, you have a floor.
Can you hear me, Chairman?
Hello.
Hello. Can you hear me?
Yes, we can hear you now. You please share your screen. It is the third button from the left side. It's screen with arrow. And once you share the screen, you may start your presentation.
Can you see the screen share?
Yes, in the not in demonstration mode. So could you launch it like yes, exactly. Please, you have a floor.
Esteemed colleagues and respected professors, I'm honored here to be here to present our latest research endeavor. Our work is called RMNet, which is a residual and multi-scale feature fusion network for high-resolution image semantic segmentation. I am the first author of this paper. observation. There are 3 people on this work, and all of us come from Nanjing Forestry University, China. Here is the content of this presentation. I will divide it into 6 sections: background, method, challenge, experiment, conclusion, and special issue. Image segmentation is a subdomain of computer vision and digital image processing, which aims at grouping similar regions or segments of an image under their respective class labels. Since the entire process is digital, a representation of the analog image in the form of pixels is available, making the task of forming segments equivalent to that of grouping pixels. And the image segmentation can be divided into traditional ways and deep learning-based ways. Traditional image segmentation originally started from digital image processing coupled with optimization algorithms. These primitive algorithms made use of methods like region growing and Snake's algorithm, where they set up initial regions and the algorithm compared pixel values to gain an idea of the segment map. These methods took a local view of the features in an image and focused on the local differences and gradients in pixels. As for deep learning-based methods, these models provide segment maps as outputs corresponding to the inputs they are fed. These segment maps are often n-channeled, with n being the number of classes the model is supposed to segment. Each of these n-channels is binary in nature, with object locations being filled with ones and empty regions consisting of zeros. The ground truth map is a single-channel integer array the same size as the input and has a range of n, with each segment filled with the index value of the corresponding classes. Semantic segmentation refers to the classification of pixels in an image into semantic classes. Pixels belonging to a particular class are simply classified to that class with no other information or context taken into consideration. High-resolution image segmentation in deep learning networks aims to divide images into different regions or objects with semantic or structural significance. This task is of great importance for applications such as image understanding, scene analysis, object detection, and image processing. In high-resolution image segmentation, the goal is to assign each pixel to its corresponding semantic category or region, thus achieving a fine-grained analysis of the image. This segmentation result provides more detailed and accurate image information, making subsequent analysis and processing tasks more precise and efficient. However, due to the characteristics of remote sensing data, semantic segmentation poses greater challenges than nature images. The challenges arise from the large data volume and high computational complexity associated with high resolution, wide range, and multispectral remote sensing images. Furthermore, remote sensing images capture diverse and complex targets, including buildings, roads, vegetation, and so on, making segmentation diverse and complex. So in semantic segmentation models, downsampling is employed in the encoder to extract features, gradually reducing the size and channel number of feature maps, leading to information loss and target boundary detail processing insufficiency, thus efficiently extracting target features, preserving them during the extraction and reconstruction processes, and minimizing information loss are crucial for achieving semantic segmentation. Therefore, we propose the RMNet. Our network is based on residual blocks and multi-scale feature fusion. The figure 1 describes the network structure of RMNet, which is referenced to UNet and consists mostly of encoder and decoder. In the encoder part, due to the high resolution and complex nature of objects in remote sensing images, our work employs ResNet50 for better feature extraction. The structure consists of a convolutional layer and 4 residual blocks. Each residual block is composed of important modules or bottleneck modules, which are concatenated optimally. The basic module uses two 3+3 convolutions and a shortcut connection to implement the residual structure. The bottleneck module reduces the number of channels with 1+1 convolution, extracts features with 3+3 convolution, and increases the number of channels with another 1+1 convolution. A 1+1 convolution is used in the shortcut connection to adjust the number of channels. The basic module is suitable for low-dimensional input data, where the bottleneck module uses more channels and fewer convolutional kernels to reduce the number of parameters and computations, making it suitable for high-dimensional input data. Therefore, in stage 2, 3 basic modules are used for shallow feature extraction, while stage 3, 4, and 5 respectively use 4, 6, and 3 bottleneck modules for deep feature extraction. The residual structure solves the problems of gradient vanishing or degradation in traditional deep networks by introducing skip connections. It accelerates the training processes, improves the network's express power, and makes deep networks easier to train and optimize. Then come to the decoder part. To generate pixel-level results in semantic segmentation, feature maps need to be upsampled to restore low-resolution feature maps to the size of the original image. Deep feature maps contains more semantic information that can be used for feature recognition and classification. Therefore, to enhance segmentation accuracy, it is necessary to consider both the low-level features and semantic information of the image. So we propose the MSFM module, as shown in Figure 3. Firstly, the feature maps are subject to deconvolution to map from low-level features to high-level features. To preserve the integrity of the low-level features, a bilinear interpolation method is utilized. Our method helps retain the detailed information of the original image. Next, the obtained feature maps are combined to yield a comprehensive and rich set of features. And our resulting feature information is concatenated with the feature information from the same layer encoder, creating a more enriched feature layer. The fusion of low-level features with semantic information provides the network with a more diverse range of channel information, which supports accurate predictions. Finally, our concatenated feature map undergoes 2 additional convolution operations to refine the feature maps and extract more valuable information, thus improving the accuracy of semantic segmentation. Here's our network's loss function. Since the majority of pixels are typically background, there is an imbalance between foreground and background. To address this issue, we adopt the dice loss function. This function focuses more on foreground region exploration to ensure a low number of false negatives, which can lead to loss saturation. Then to mitigate this saturation issue, we combine the focal loss with the dice loss. The final loss function is the equation 1. In equation 1, the lambda represents the coefficient of focal loss in the whole loss function. And in our experiment, we set lambda to 0.9. Equation 2 is the expression of dice loss, where the absolute value of the x and y present number of predicted and true values respectively. while the absolute value of the intersection of x and y represents the intersection of predicted and true values. The parameter s is introduced in the formula with a value of 10 to the minus 5th power. It helps prevent overfitting. The last equation is the expression of focal loss, where pt represents the probability of correctly classifying the predict sample, while both alpha t and gamma are adjustable factors. We set alpha t and gamma to 2 and 0.25 respectively. In the experiment, we start with the WHDLD dataset. It is a collection of 4940 RGB images captured by the Gaofen 1 and ZY3 satellites, specifically focusing on the Wuhan urban area. It contains 6 types of remotely sensed feature types, extracted from USIMMERSE and released by Wuhan University in 2018. The targets are divided into bare, building, pavement, road, vegetable, and water. In order to verify the effectiveness of the method, we compare and analyze ARMNet with common semantic segmentation models, in which all network models are trained with an epoch of 100 and save the optimal weight file obtained after the training is complete. The prediction was performed on the test set. Figure 4 shows examples of WHDLD images and their corresponding ground truth, while Figure 5 shows the prediction results of different methods and ablation experiment. In the Figure 5, the CNET means our model without the introduction of both modules, and it is referred to as a normal convolutional network. The effectiveness of the network for segmentation of detailed regions and its vulnerability to segmentation leakage were observed after removing the MSFM module. This suggests that the integration of low-level features and the fusion of low-level features with semantic information are essential for achieving effective semantic segmentation. The removal of the RBM module leads to rougher segmentation results, increased leakage, and incorrect segmentations, indicating the model's suboptimal performance. These two tables show specific experimental data for our network. Table 1 shows the experimental results of different models on WHDLD, while Table 2 shows the F1 score index results of each category of the experiment. In both two tables, the larger the value of each indicator, the more effective our model is. So from the results of the previous experiments, it can be concluded that our network has several advantages. Firstly, it significantly improves segmentation accuracy and the ability to locate and segment the target accurately. Secondly, it reduces false detections, thereby filtering background interference and improving the reliability of semantic segmentation. Additionally, the network maintains a fast processing speed while achieving high accuracy, enhancing its real-time performance and making itself more robust. Finally, I would like to present a program sponsored by my supervisor and his colleagues. It is about pantomic segmentation to train things from mobile LiDAR data, and we are looking forward to your submissions. Thank you for your listening.
Thank you for your presentation and for providing us information about your place for publishing our results. Please, currently we have a couple of minutes to ask and answer both questions. We have none. Okay, thank you again. I have also none of questions, and yes, thank you for stop sharing the screen. Now we come into the end of this session finally and successfully. And the last but not least, Mikhail Kharinov, please. Now the floor is yours. Share your screen if you really know how to do this. Okay. Yes.
Слышно, да?
It is okay. Yes.
Все. Можно начинать, да?
You may start if it's possible to talk in English. Is it possible? Because we
Yes.
have.
Okay.
Yeah.
My name is Mikhail Kharinov. I am an employee of the St. Petersburg Federal Research Center of the Russian Academy of Sciences. My report is about calculating optimal image approximation for computer visions. That is NP-hard problem. Since the problem is NP-hard, it can only be solved if the image model is successfully constructed. Все, спасибо. Conceptually, we believe that the visual system of a person, or say a fly, sees optimally. That is, evaluates optimal image approximations. The novelty of the work lies in the fact that we take classical methods of cluster analysis and follow the established invariance requirements. But at the same time, we check how this method should be applied in new conditions that have changed with the advent of computers. The current state of the work is reflected in the series of papers in journal Imaging. The slide describes the image through the sequence of its optimal approximations. The dependence of the approximation error on the number of colors in the image is shown. The limiting lower curve describes the error of optimal image approximations. It is assumed to be convex, which is verified experimentally. The convex red curves show the hierarchies of approximations corresponding to the objects. Each hierarchy of objects contains at least one optimal approximation, at least the red curves touch the gray curve at least at one point. The top black curve describes an unstructured hierarchy of image and object elements called superpixels. Such approximation of an image by numerous object hierarchies exists. All that remains is to learn how to calculate it. This slide lists the main disadvantages of classical clustering methods in computer processing of big data. This is not what is written in Wikipedia and other more reliable sources. Watt's method is the main one. It has been established that the approximation errors are unstable for each number of colors. Moreover, due to multi-iterative calculations, the approximation error changed with slight modification of the image or change in the order of scanning cluster pairs. Established instability turns into a property of variability, which is actively used if Watt's method is used in combination with Monte Carlo method. Slide explains the modernist methods and their working formula. Above is Watt's method and the main formula from which the others formulas are derived. The modernizations is reflected in the method name. What method is applied to subset of pixels into which the whole set of image pixels is divided. This solves the problem of speeding up calculations. Slide on the left shows the output data using an example image of 25 pixels. This is a typical network thrown over the image pixels. The network is formed by Slater-Taryan dynamic trees, black arrows, and cyclic graphs, red arrows. The latter specifies the order in which three arcs are established. The arcs of the Slater-Taryan dynamic tree are indexed by increments of the approximation error. The figure on the right, using an example of a 4-pixel image, explains how such a network is obtained. It is obtained by merging trees and cyclic graphs. When merging trees, the root nodes are connected by an arc. When merging and splitting cyclic graph, certain nodes simply exchange their pointers. This slide shows several sequences of optimal approximations with overlapping clusters of pixels. Above are the optimal approximations of a grayscale image obtained and published 10 years ago. The rest is the optimal approximation of a color image, just that we can compute within the limits of visual indistinguishability. This slide presents so-called dynamic table of image approximations, in which the approximations themselves are replaced by standard deviation values. Hierarchical sequence of approximations are arranged in columns. Repeating columns are omitted. The red cells occupy the optimal approximations with the minimum standard deviation values within the rows. The computer analyzes this table. The software engineer analyzes the approximations themselves using invariably colored objects. His first task is to select a suitable hierarchical object coloring so that the computer sets the appropriate parameter to select the desired object hierarchy. Slide shows the speed up of calculation by about 1,000 times due to the use of Ford's method by parts of the image. The thick black curve shows the dependence of approximation errors on the number of colors for optimal approximation obtained as a result of time-consuming calculation using a trivial method. The white thin curve shows the dependence of the approximation error for the case of dividing the image into 10 parts, which are first processed as an independent image, and then the resulting approximation hierarchies are glued together. It is noteworthy that the curves are almost identical. Also, the algorithms are quite different. The coincidence of these results confirms their reliability. This is the final slide about the implementation of our work. The point is this. We have a program for generating optimal image approximations. It seems to us that no one has such a program yet. If someone seems interested in trying it out in practice, we will be happy to cooperate. Thank you for your attention.
Okay, many thanks for your presentation. Okay, so we have question please. You may ask question now.
You listen me?
Yes.
You do hear? Mikhail, please, some comments about speed of algorithm when you deal with images, not train data, but in approximating. When you approximate it, how fast
The problem of speed is obvious. When the number of pixels grows, then the number of pairs grows quadratically. And when we divide image into parts, if we divide image into 10 parts, then the number of pairs fall down 100 times. And by dividing image into parts, the problem is solved. But many pairs we omitted. And the main result of our experiment is that this omitting pairs does not destroy the result. We obtain the same result as we take as if we take in the account of all pairs for whole image. Is it clear?
Okay, thank you. Thank you. Very interesting.
Yes, they're very classical and interesting at the same time. Okay, well, other questions? We have none. So, dear colleagues, I would like to announce now the end of this session, and we'll make some summary. Please stop sharing the screen. Yes. Okay. Well, we successfully finished the session, I think, and because we actually have 6 reports of 7. And now we have some break. You may leave the session or may be with us, because next session will be on the same platform with the same account, and on YouTube it is a non-stop broadcasting. So okay, thank you all of you, and see you, I hope, offline, in person, in Minsk or somewhere, so to do science. Thank you all. Okay, dear colleagues, now we come into the next session, next online session, but now I'd like to know who is online from the session 02. Please switch on your mic if you're from the session 02.
I'm not too, but I'm here.
Yeah, that's I see. Thank you. So actually, we have 6 presentations which must be in this session 02, but I see none of presenters. Okay, well, colleagues, we have 2 options now. We can still wait for a couple of minutes for those who would like to attend the session and to present their paper, because actually, so it's very important to be in proceedings, and probably after the conference, organizers will decide what the paper will be included in the Springer's book, pattern recognition, image analysis. But now we need to fill the gap, and if somebody of you who now in online want to present some ideas or any advertisement, research advertisement, or research ideas, and we can just discuss. We can do it in any mode, any manner, in roundtable, in a presentation mode, in any. So what would you suggest? Still, we have time and we need to fill the gap.
In my view, the round table is a good idea. So for instance, we can ask everyone who is present here to answer what is the most interesting direction of future development in our field from that person point of view. Yeah. So what is most interesting looks like? It appears to be.
Yeah.
Topic.
Yes. I think yes. Well, it's a very nice idea. So we have Jihad here. We have
Alexei, you disappear somehow.
Yes, exactly. So connection troubles. Yeah. Well, so I was absent just in a couple of seconds, but still nobody from the second session here. Okay, we'll have here at least 3, including me. Well, 4. Table, let's say, attendees, and we can discuss. And if Ivan and Jihad would like to also to attend this round table, we can do this. What about you, Ivan Lipko? Do you hear me now? Well, I think none. Well, in this case, actually, so there is no round table because we're just 2 of you. Yeah. In this, let's say, in this way, on premises of organizers, on behalf of organizers, and as the chairman, I need to stop this session and to stop broadcasting to YouTube. Well, if you not. If you have other ideas, we can just finish the session. That's all.
No ideas.
No ideas. Okay.
No.
Let me announce that the first day of hybrid conference of the session 0102 is finished. Now, see you, all of you, and those who is on YouTube. I think next time will be many more attendees who would like to present their papers, and if it's possible. Well, now it's possible to make roundtable, but no any other attendees here. Okay, Dr. Vasily Kovalyev, I would like to thank you many huge thanks, because we need to fill this gap, and so we're here. And so I know that you also co-organizer of the conference, and thank you for your plenary report. It was nice, and I hope it will be also seen on Facebook, or no, on YouTube, probably Facebook also. But anyway, so any platform what we will include to our platform. Okay, see you.
Okay, thank you very much. Bye for everyone.
Yeah.
Bye.
Bye.
Bye.